Alright, year 12, we are going to look at a thing called eddy currents, back EMF, and Lenz's law. So, the dot point we're covering is in Module 6, Inquiry Question 3, Number 2, Analyse the qualitative and quantitatively with reference to energy transfers and transformations, examples of Faraday's law and Lenz's law. Today's scenario we're going to look at is for straight line conductors, and then we'll do one for solenoids. So we are looking at this one here. It says the generation of an electromotive force and evidence for Lenz's law produced by relative motions between magnets, straight conductors, metal plates, and solenoids. So we're going to look at this one here, and then we can look at the two different solenoids later on. Scenarios, here we go. Okay, Lenz's law is essentially stating that an induced EMF will create a current that produces a magnetic field that exerts a force which opposes the change that causes it. So to illustrate that, and probably show you as a demonstration later on, we have a north pole that is coming towards our solenoid, going this way here. Now, according to Lenz's law, whatever current I generate, that current is going to generate another magnetic field that tries to push this magnet away. Now, we know that if we have two similar poles, two north poles, their magnetic fields can never touch. They basically spread out like that. So that's kind of what Lenz's law is trying to state, that when we have a change, when we have an induced EMF, it will try and oppose the original change that caused it, mainly by having a current moving in the opposite direction and a magnetic field that goes in the opposing direction. Now, there's a couple of names we can call this. An induced EMF can also be called the back EMF, so it's going the opposite direction. And also, the current we create is also known as the induced current. One of the later examples we'll look at, eddy currents, is an example of an induced current. Okay? So that's what we're looking at here. Now, the quest of understanding, we're not going to look at the energy transformations, whatnot, just yet. We are going to focus solely on how to identify the direction of the back EMF, or the induced EMF, and also the direction of the force or magnetic field that's induced to oppose the original change that we have. That's what we're going to be looking at today. Mainly for straight conductors, and then we'll go into solenoids. Okay, so this diagram here, I guess I'll just focus on A, because B and C are following up on A, so easy to go for that. So we have a conductor that's being pulled downwards. Okay, that's our scenario here. I'll do it in blue. So if a conductor, this is our straight line conductor, okay? If it is moved downwards, that means the force applied on it is down, okay? You can imagine this with your right hand. Remember, your right hand palm rule, okay? Your right hand palm rule. Oh, I keep drawing my left hand when I talk about this. Fingers, palm. That is force, that is direction of magnetic field, and that is direction of charge, positive charge, okay? Now, according to Lenz's law, the motion that I have right now is a force going down. So according to Lenz's law, and I'm going to do this in red just to differentiate, I'm going to generate a force that goes in the opposite direction of the original motion. So if the original motion was going down, the induced motion of force is to go up. That's how Lenz's law defined it. Okay? That's how Lenz's law defined it. So if the induced force is to go up, and the magnetic field I originally had was going into the page, if you use your right hand rule, okay, your thumb is pointing to the right. And so that's the direction of our induced current. That's the explanation of how to work this out. Okay? But there are other ways you can do this as well. Okay? So that's the first way. If you didn't want to work out where the induced force was going, so say you just want to work out where the induced current is without considering force, then again use your right hand. Force is going down the page, so that's the, well, that's not induced, that's the original. So the original force is going down the page. The original magnetic field is also going into the page. Okay, so your right hand, if you use your right hand for scenario B, force is coming down the page, palm pointing down, finger is pointing in, thumb is actually pointing to the left. Okay, now that scenario would be if we were just generating current. That's the interaction. But because it's an induced current, you flip your right hand over, and then from that being your thumb going to the left, it's actually going to the right. So that's another way of doing it. One is to find the induced force and work it out that way. The other is to use two known variables that you have, and then you just flip your right hand around. The last one you can use is your left hand rule. So your left hand, because it points of a different polarity, your left hand, okay, so your left hand, in other scenarios we used to say that the thumb of your left hand is acting like a negative charge. Well, by definition, we are generating a back EMF, so the back EMF is going in the opposite direction of what we originally had anyways. So you can actually use your left hand to work out the induced current as well. So using the exact same example we have here in C, the conductor is going down the page, magnetic field is going in, so left hand, palm pushing down, fingers going in, thumb, left thumb that is pointing to the right. So there's actually three ways you can work this out. Generally speaking, if you understand the philosophy of what I talked about for scenario in the A section there, you can just use your left hand to help you work out the back EMF or the induced current. Okay, so it's quite important that you remember what the right hand palm rule is. Fingers, direction of the North Pole, or the direction of the field. F is or your palm, perpendicular of your palm, direction of force, and thumb is for the current, and that is for a positive current. Later on, we're going to look at circular conductors, so solenoids, and that's going to use the right hand grip rule. Your fingers is the direction of the current, and direction of your thumb is kind of like your North Pole, also direction of where the magnetic field is going. Okay, so how do we apply Lenz's law to identify induced current? Using the right hand palm rule. You can use the right hand palm rule to find the two known variables first in a given question, and then find out its direction from the third after you have, and then reversing that direction there. Okay, so there's that. Now, I do want to emphasize one point that's very important. The right hand palm rule is a guide. Okay? Lenz's law is the explanation of why we have an induced current. So in any question you have where it says, how do you know where the induced current is, technically you should be speaking about Lenz's law to guide you to explain where the induced current is. The right-hand palm rule is just a guide to assist you in that, but it doesn't actually explain why it does that, okay? So be very careful about that when you're writing your response. Okay, let's look at these scenarios here. So the first one, we're trying to find the direction of the induced current. Okay, I'm just going to go through a bit of a longer method because I think it's quite important for you to understand. You can just use your left hand and it'll do the same thing, by the way, or flipping your right hand already. But I just want to go through the actual logic for maybe the first two, and then we can go through using our left hand to solve it. So big V here, don't worry about that, just assume it's the force of pulling the conductor down. So the palm of your hand, is pointing down. Your fingers are going into the page, okay? So that's what we know. That's the original force. The induced force should therefore be going up the page. Okay, so using my right hand, fingers are pointing into the page, induced force is going up the page. So induced current is going to the right here. Question B, these dots represent that magnetic field is coming out of the page. The conductor is coming toward or moving towards the right hand side. So the induced force, or according to Lenz's law, the induced force to oppose this would be to move in this direction. Which means, using your right hand, fingers pointing out of the page, palm following where the induced force goes, going to the left, hence thumb is pointing down, so the induced current is going down the page. If you look at C, the force of the conductor and the magnetic field is in the same or in parallel direction to each other, so nothing happens there. Okay, now let's look at D. Let's use our left hand to help us do the exact same thing. Okay, remember the left hand already takes into account that it is a induced current or back EMF. So on D, the magnetic field is going to the right hand side, so fingers pointing to the right. Okay, the force being applied on the conductor is pushing it upwards. So according to my left hand, which already considers the opposite or the reverse direction, my thumb is pointing into the page. So the current is going into the page here. Okay, next one we have is E. Okay, so conductor is going to the right, so left hand palm is moving facing the right hand side. Magnetic field is pushing up the page. So what we see is my induced current, which is my left thumb, is coming out of the page. Okay. Question F. The force on the conductor is going to the left. Okay. And the magnetic field is coming out the page. Okay, so according to my left thumb, the induced current is going up. Okay, and that should match all the answers that I said there. Wonderful. Okay, the next method we'll try is just to use our right hand, but not looking at the induced force. We'll just use our right hand to work out where the changes are. So we have a current in scenario A Okay, so in scenario A, my right hand thumb is pointing out the page, okay, pointing out the page, and the fingers I have is pointing down the page. So my right hand is facing, the right palm is facing the right hand side. Okay, so because this is an induced current, the force that this thing experiences is going to the right, so that's the induced that it's creating. So the force here is the induced side. So the originals would have to be going in this direction. Okay? So let's check that out. Exactly. B. Our current is going to the right. My magnetic field is going into the page. So my induced force is going up the page, which means, according to Lenz's law, that is trying to oppose the original change. So that means the original force would have to be coming down the page. Okay. C. Thumb coming down the page, fingers pointing out of the page. The induced force is going in this direction, which means that the original force is going in that direction. Okay? D. Thumb is going into the page because it's the current. Magnetic field is going to the left. So the induced force is going up. And the original force is coming down. That's the logic we have there. Okay? In question E, the original force was going into the page, and in F, the original force was going out of the page. In question 3, it's asking you to find the original direction of the magnetic field. Okay? So again, you can use your left hand to help you out. Using my left hand rule, current is going to the left, force is going down, into the page. B, up. C would be to the right. D is out. E is to the left. F is going to the left as well. Well, E is going right, F is going left, and G is going up. Okay? What about a scenario where it is asking for electrons? Okay. This one's an interesting one. You can see some of the doodles I've already done here. All the scenarios we've talked about have been for positive charges. Now, an electron is a negative charge. We have a south pole, and south pole, how magnetic fields work, it goes from north to south. So it goes from north to south. So that's why I drew magnetic fields going into the page like this. We have a force on the plane that is going up. So this is our original force. So whatever's happening, the induced force should be going in the opposite direction. Okay? Should be going in the opposite direction. Now the question is, what hand should we use? Well, you can use either one. It does the same thing. Now, if you use your left hand, which we use to describe negative charges, your thumb is, or the original force is going up the page. So your left palm is going up the page. Your fingers are going into the page because that's the south pole. Your thumb is therefore going to the left. Okay? But because this is an induced force we're looking at, we can see that the induced force is pointing down. So left hand down, fingers going into the page, thumb is pointing towards the right. Okay, so in this scenario, the induced electrons, or the electrons, will experience the motion moving to the right because of that induced force there, and that's why it's that instead of the left. And the reason why we flip our left hand this time is because we are dealing with negative charges. Similarly, if you're dealing with negative charges, if you want to find the induced EMF of negative charges, you could just use your right hand to do the exact same thing. That should be B here. So it shouldn't be left. It should be B. So that's the wrong answer. Okay, so here's some notes here. And these are some other scenarios of how to do Lenz's law for straight conductors. So make sure you have a go at these at your own time. And if you're not sure, please always ask. So that's it to end this particular part here. We are ending it at straight conductors. But we will go into a second video that looks into solenoids. So until then, keep practicing your Lenz's law. Use the right hand palm rule. Okay. Always remember to use the two known variables using your right hand. And then for the third one, find it and then reverse it. Or the other way of doing it is the left hand palm rule and use the two known variables. And then the last variable to detect where the backwards or the induced / original came from. Okay, so that's the difference between the two. Don't get them confused. And remember, at the end of the day, both of these rules are just guides. The thing that really governs how these all work is Lenz's law.